This video is going to talk about similarity. Now, in the last video, we talked about scale modeling, and scale modeling introduced the concept of geometric similarity. So you'll recall we had a model, and all of the dimensions of the model are designated with a subscript m, and we had a prototype, which generally is a larger size, and all of the dimensions are designated with a subscript p. So the concept of geometric similarity means that any ratio of dimensions between the model and the prototype is the same. And as we said at the end of the last lecture, sometimes that's a little bit difficult to achieve, but in most scale model studies, we can do a good enough job of it that whatever we learn by studying the model, we can apply to the prototype. So geometric similarity is at the heart of scale modeling. Now, there are other types of similarity that we must also respect in order to do scale modeling. And the next one we'll look at is called kinematic similarity. So here, let's say that we're trying to measure the forces on a new airfoil design by constructing a small model of that airfoil and putting it in the wind tunnel and measuring the forces on it. So here's our model, and here's our prototype. Well, there's going to be some free stream velocity in the case of the model. So the air velocity in the wind tunnel is designated here U sub m, the free stream velocity for the model. Now for the prototype, in general, there's going to be a different velocity. So kinematic similarity refers to the ratios of velocities between the model and the prototype. So if we look at a particular spot near the surface of the model, then we'll have some velocity there. So point 1 is that particular spot. The velocity, which remember is a vector, at point 1 on the model is designated by this. If we go to that geometrically similar point on the prototype, there will be some other velocity designated v1 of the prototype. Well, kinematic similarity says that all velocities have the same ratio. So that means that the ratio of the velocity at that particular point on the model and prototype has to be equal to the ratio of the free stream velocities. So that's kinematic similarity, velocity ratios of the fluid between corresponding points on the model and the prototype have to be the same no matter what 2 points we take. So kinematic similarity. So geometric similarity has to do with physical dimensions. Kinematic similarity has to do with the velocity of the fluid. The last of the three types of similarity that we're introducing is dynamic similarity. So here again, the illustration we're going to use is a model study to measure the forces on a new airfoil design. And one of the forces that we might be interested in looking at is the lift force. So because of some pressure distribution and shear distribution around the surface of this object, there's a lift force generated under some conditions. And so that's designated here as the lift force on the model. Well, there's also a lift force on the prototype. We may also be interested in the drag force. So lift force is a force perpendicular to the free stream, and a drag force is a force parallel to the free stream. So there's some drag force on the model and some drag force on the prototype. Well, dynamic similarity is achieved when all force ratios are the same. So the lift force on the model divided by the drag force on the model must equal the lift force on the prototype divided by the drag force on the prototype. So measurements that we make of these forces on the model can be used to predict measurements of those forces on the prototype as long as we have similarity achieved. So that's an example of dynamic similarity. So as an example, just carrying this on, let's say that we are measuring the drag force on a new airfoil design. So we have a model and we want to use measurements on the model to predict what's going on in the prototype. So the dimensionless groups between these two situations must be equal. Now, in the next lecture video, we're going to talk about how to come up with those dimensionless groups, so we won't worry about that just now. But if we go through that process that you'll learn in the next video, we would come up with a relationship like this. It would tell us that this dimensionless drag force is equal to this particular dimensionless number. Okay? And we're going to go through this process of developing this equation in the next lecture video. But drag force divided by rho v squared c squared equals a function of, or is a function of, rho v c over mu. Well, first of all, I need to tell you what this c is. C is the chord length. So that's the distance from the tip of the airfoil to the trailing edge. So that's C. So the prototype has a chord and the model has a chord. And of course, geometric similarity means that the ratio of those chords would be the same as the ratio of any other dimension in this problem. So that's a dimensionless drag force, and it's a function of this thing. Well, if you look at this, this is a Reynolds number. Although instead of the pipe diameter, which is irrelevant in this problem, there is no pipe, our characteristic length is the chord of the airfoil, C. So this is what dimensional analysis will tell us. Well, scale modeling and similarity tells us that if the right-hand side is the same between the model and the prototype, so the Reynolds number of the model equals the Reynolds number of the prototype, so if this number is the same, then it doesn't matter what this function looks like. It could be a very complicated function, but if that is the same, this is the same. So similarity says that if the Reynolds number between the model and the prototype is equal, then the dimensionless drag force between the model and the prototype is equal. So this is the power of similarity and the power of scale modeling. It means if we can set up an experiment where the Reynolds number on the model is the same as what the full scale object is going to have, and we make a measurement of the drag force on the model, which is relatively easy to do, we can predict the drag force on the prototype. And this is what we're really interested in, the drag force on the full scale object. So therefore, we can predict the drag force on the prototype by measuring the drag force on the model. And similarity is what allows us to do that. So like I say, in the next lecture video, we'll be showing you how to come up with these groups of variables that form dimensionless groups. But once we've done that, scale modeling becomes possible. Now, before we head off into that lecture video, there's just one other topic that we want to introduce here, and that's the principle of dimensional homogeneity. Because the process that we're going to look at to come up with dimensionless groups really depends on this principle. Well, what does it say? Well, it says that equations that describe physical processes, so essentially all the equations we're dealing with, must have the same dimensions for each additive term. Now, you've probably heard this principle before, and in practice we use this all the time because we tell you to check the units of your equations to make sure that the units of every term in your equations is the same. And you can prevent a lot of little numerical errors by doing that. So if we take a look at Bernoulli's equation, the principle of dimensional homogeneity tells us that the units of every one of these terms has to be the same, or the dimensions of every term has to be the same. So what are those possible dimensions? Well, in this class, there are 4 fundamental dimensions involved. So mass, length, time, and temperature. And the symbols that we're going to be using as we go forward for these are capital M, capital L, capital T, and because we use T for time, we can't use it for temperature, so we use this uppercase theta for temperature. Temperature is not a very important variable in this course, so primarily it's the first 3 of those that we're going to be using. So realize these are called the dimensions, and these are different than units, right? Units, if we were talking about SI, would be kilograms, meters, seconds, or degrees C. Those are units. What we're talking about in this class is dimensions. So the dimensions of mass, for instance, could be described by many different units: kilograms, slugs, pounds mass, whatever system of units we happen to be using. This terminology around dimensions here is independent and more general than any particular unit system. What we're going to look at in the next video is something called the Buckingham pi theorem. And that's the process we go through in order to generate these dimensionless groups. So we'll see you in the next video.